somewhere in the future, so far ahead that the number of years required to describe it would fill this page 1,000 times over. The last star in the universe will die. There will be no one to see it happen. No telescope pointed at the sky. No civilization watching from a distant world. Just a single dying ember of light, cooling slowly in a darkness so complete that nothing warm exists anywhere, in any direction, across the entire observable universe. And then it will be gone. What comes after that moment? What the universe becomes after its very last light source fades, is one of the strangest, most quietly unsettling ideas in all of science. Not because it threatens us. We will be long gone, impossibly long gone, before any of this unfolds. But because it reveals something profound about the nature of everything, about time itself, about what the word forever actually means when you apply it to physics rather than poetry. Tonight, we are going to follow that story, not just the story of a dying star, but the story of all stars. Where they came from, why they exist at all, what forces keep them burning, and what forces eventually extinguish them. We are going to move through time in a way that almost no other subject allows. Not millions of years, not billions, but trillions upon trillions of years into a future so vast that our entire cosmic history so far occupies only the very first breath of it. By the time we reach the end of that journey, you will understand something that very few people have ever sat with long enough to truly absorb. Stars are not permanent. The universe itself is not permanent. And the timeline on which everything we have ever known or loved or imagined exists is, by the standards of deep time, almost impossibly brief. But we need to start much closer to home. Because before we can understand the last star, we need to understand what a star actually is, and why the universe made them in the first place. For the first few 100 million years after the universe began, there were no stars. Think about what that means for a moment. The universe existed. Space was expanding, matter was present, energy was everywhere, and yet the sky was completely dark. Not dark in the way a cloudy night feels dark. Completely, perfectly dark in every direction, with no source of light anywhere in existence. The cosmos was filled with hydrogen gas and a small amount of helium. And that gas was slowly cooling, slowly falling together under gravity and waiting. Astronomers call this era the Cosmic Dark Ages. It lasted somewhere between 150 million and 800 million years. Precise measurements are difficult because there was nothing to observe. Light itself could not travel freely through the dense plasma of the early universe, and the cooling gas that followed left few fingerprints. We know the Dark Ages existed the same way a detective knows a room was once occupied. Not from watching it happen, but from reading the evidence left behind. What ended the Dark Ages was fire. Specifically, the first ignition of nuclear fusions inside a cloud of collapsing gas. When gravity pulls enough hydrogen together into a tight enough space, something remarkable happens. The pressure at the center becomes so extreme, and the temperature climbs so high, tens of millions of degrees, that hydrogen atoms can no longer simply bounce off each other. They collide with enough force to fuse. Two hydrogen nuclei merge into helium, and in that merging, a small amount of mass is converted directly into energy. The energy radiates outward. The first light in the universe was born. This moment, this first stellar ignition, was not a single event. It happened across the universe over millions of years, in different places, in different clouds of different sizes. But the result was always the same. A ball of gas that had been dark and cold and quiet became luminous, and the universe, for the first time, had stars. What is striking about that first generation of stars is how different they were from anything that exists today. Astronomers call them population 3 stars, and they were unlike almost anything in the modern universe. With no heavy elements to cool and fragment the gas clouds, because heavy elements had not yet been created. Those first stars were enormous. Some theoretical models suggest individual population 3 stars may have been hundreds of times more massive than our Sun. They burned with extraordinary ferocity. They lived fast and died violently, and in dying, they scattered the first heavy elements, carbon, oxygen, silicon, iron, across space. Every atom in your body, heavier than hydrogen, was forged inside a star, not the same star. Many stars across billions of years, each one contributing to the slow enrichment of the universe. Each one leaving behind the raw material for the next generation. Stars are not just sources of light and warmth. They are the universe's factories, the only places in existence where matter transforms into new matter, where simple elements become complex ones, where the ingredients for planets and oceans and living things are assembled from something as elemental as hydrogen gas, which makes a question worth sitting with rather carefully. If stars are the factories that make everything, what happens to the universe when the last factory closes? Before we move forward in time, it is worth understanding the fundamental tension that governs every star's existence, because it is that tension and the way it eventually resolves that determines not just how stars die, but when and in what sequence, and ultimately which star will be the very last one standing. A star is a battle between two forces that are trying to do opposite things simultaneously. Gravity wants to pull everything inward. It is relentless. It does not tire. Given enough time, gravity would collapse any mass of material into the smallest possible volume. If gravity were the only force at work, the sun would collapse on itself in about half an hour. But gravity has an opponent. At the heart of every star, nuclear fusion releases energy, and that energy pushes outward. It creates pressure. It resists gravity's pull. As long as fusion continues, the star maintains what astronomers call hydrostatic equilibrium, a precise balance between the inward crush of gravity and the outward push of energy, maintained second by second across the entire interior of the star. What makes this balance remarkable is how sensitive it is. If the star somehow produces too much energy, it expands slightly, which cools the core, which reduces the fusion rate, which reduces the outward pressure, which lets gravity recompress it, until equilibrium is restored. If the star somehow loses energy too quickly, it contracts slightly, which heats the core, which increases fusion, which pushes back outward, until equilibrium is restored again. The star is constantly self-correcting. A thermostat billions of kilometers wide, with a nuclear furnace at its center. This balance is what makes starlight possible, and it is the fuel that powers the balance, hydrogen, that determines how long any particular star can shine. Here is where something surprising enters the picture. You might assume that the most massive stars, the ones with the most fuel, live the longest. In almost any other context, this would be a reasonable assumption. More resources usually means longer survival. But stars do not work this way. The most massive stars die first. The reason is that more massive stars have more gravity. More gravity means higher core pressure. Higher core pressure means higher core temperature. Higher core temperature means faster fusion. The fuel burns at an extraordinary rate. A star 10 times more massive than the Sun might exhaust its hydrogen supply in 10 million years, 1,000 times shorter than the Sun's expected lifespan. A star 50 times more massive might burn for only a few million years. Meanwhile, at the other end of the scale, the smallest, faintest, coolest stars in the universe, the ones called red dwarfs, burn their hydrogen so slowly, at such low temperatures, that they can shine for trillions of years. Some red dwarf stars that exist today have barely consumed a fraction of their fuel. They are, in cosmic terms, barely getting started. This asymmetry is fundamental. It is the reason the last star in the universe will not be anything spectacular. It will not be a blazing supergiant. It will not produce dramatic jets, or pulsar winds, or the spectacular nebulae that result when massive stars end their lives. The last star will be one of the most modest, unassuming objects in existence. A red dwarf. An ember, barely bright enough to be called a star by our sun's standards. But that ending is a very long time away. And to understand what leads to it, we need to understand what comes before it. The slow, inevitable decline of the universe's star-forming ability. Here is something that almost no popular account of astronomy makes clear. And that changes the way you see the night sky permanently once you understand it. We are not living in the middle of the universe's star-forming era. We are living near the end of it. The universe reached its peak rate of star formations approximately 10 billion years ago. At that time, roughly 140 times more stars were being born each year across the cosmos than are born today. The universe was ablaze with new stellar ignitions. Giant star-forming regions filled entire galaxies. The night sky, had anyone existed to observe it then, would have been thick with luminous nebulae and young, brilliant stars. Then it began to slow down. The reason involves the fundamental resource that all star formation requires: cold gas. Stars form when vast clouds of hydrogen gas collapse under gravity, fragment into clumps, and eventually compress enough to ignite fusion. For this process to work, the gas must be cool enough to collapse. Hot gas has too much internal pressure and resists gravity, and over billions of years, the universe has been slowly running out of cold gas, suitable for star formation. Some of this gas has already been incorporated into existing stars. Some has been heated to millions of degrees by energetic events, supernovae, active galactic nuclei, the violent processes associated with galaxy mergers, and now sits too hot to collapse. Some has been expelled from galaxies entirely by those same energetic events, scattered into the vast emptiness between galaxies where gravity cannot gather it back. The result is a universe in slow decline, not a dramatic collapse, not a sudden cessation, but a gradual, prolonged fading, like a bonfire that is no longer being fed. Still burning, still bright by any practical measure, but consuming its reserves rather than being sustained by new fuel. Today, the universe forms approximately 1 or 2 new stars per year per galaxy. Some galaxies form fewer. Some, though still rich in gas and experiencing gravitational interactions, form more. But the overall trend across cosmic time is downward, and has been downward for 10 billion years. This has a profound implication for the future. The total number of stars that will ever exist in the universe is probably around the same order of magnitude as the number that exists right now. Perhaps 2 or 3 times more stars will form before star formation essentially ceases. But the great era of stellar creation, the era that produced our sun, our solar system, the chemical complexity that allowed life to arise here, is already winding down. We are living in the late afternoon of the universe's stellar day, and the night that follows will be extraordinarily, almost incomprehensibly long. Before we move deeper into the future, it is worth pausing on the question of scale, because everything that follows involves timescales so vast that human intuition becomes genuinely unreliable, not exaggerated. Genuinely unreliable in the way that trying to visualize a color outside the visible spectrum is unreliable. The universe is approximately 13.8 billion years old. The Earth is approximately 4.5 billion years old. These numbers feel large, and they are. But they are manageable in comparison to what comes next. The Sun has about 5 billion years of hydrogen burning left before it begins to swell into a red giant and eventually sheds its outer layers, leaving behind a white dwarf. 5 billion years. That is longer than the Earth has existed so far. But the smallest red dwarf stars, the ones that will outlast everything else, have lifespans measured in trillions of years. Not billions, trillions. A star with about 8% of the Sun's mass may have a lifespan exceeding 10 trillion years. That is roughly 1,000 times longer than the current age of the universe. Useful way to think about this. If the entire current age of the universe, 13.8 billion years, were compressed into a single day, then the lifespan of the longest-lived red dwarf star would represent roughly 725 days, nearly 2 years. What we think of as deep cosmic history would be the first 90 seconds of that span. Even that comparison undersells it. Because after the red dwarfs die, after the last stellar light goes out, the universe continues. For an incomparably longer time, it continues as a dark, cold, slowly decaying place. The era of darkness, after the last star dies, will make the era of stars look like a brief, almost accidental episode. Physicists who study this future have developed a classification system for cosmic time that uses powers of 10 as its units. They call this the cosmic calendar of the future. Though calendar implies intervals that human minds can grasp. In this system, the current age of the universe corresponds to roughly 10 to the power of 10 years. 10 billion years. The death of the last red dwarf star occurs at around 10 to the power of 14 years, 100 trillion years from now. Beyond that, the era of white dwarfs cooling and fading, the era of black holes. The incredibly remote era, in which even black holes eventually evaporate. Each of these eras is longer than the last, separated by gulfs of time that make the entire stellar era, the era in which any star anywhere is burning, look like a single spark in an otherwise dark room. We will come back to all of that. But first we need to understand the sequence of extinction that leads to the last star. Stars do not all die at once. They die in sequence, ordered almost entirely by mass. The most massive die first, quickly and dramatically. The medium-mass stars, the Sun's approximate cousins, die on timescales of billions to tens of billions of years. And the smallest stars die last, quietly, over times that dwarf everything that came before. Understanding this sequence is key to understanding why the last star will be what it will be. The most massive stars, those 10 to 100 times the mass of the Sun, exhaust their hydrogen in millions of years, then burn through progressively heavier elements in the attempt to keep fusion going. They fuse helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Iron is where stellar nuclear fusion meets its hard limit. Fusing iron requires more energy than it releases. When an iron core builds up at the center of a massive star, fusion ceases in that region. Gravity wins, instantly and catastrophically. The iron core collapses in less than a second. The outer layers of the star, falling inward, strike the collapsing core and rebound in one of the most energetic events in the universe. A supernova. A single supernova briefly outshines an entire galaxy of hundreds of billions of stars. It releases more energy in seconds than the sun will radiate across its entire 10 billion-year lifetime, and it scatters the contents of the star, including all those heavy elements forged in its core, across interstellar space, where they become the raw material for future stellar generations. The most massive stars die like this throughout the early and middle history of the universe. But as the most massive stars are extinguished, the average mass of remaining stars declines. The universe gradually shifts from being dominated by brilliant, short-lived giants to being populated by quieter, longer-lived objects. Stars like the Sun occupy a middle range. The Sun, a comfortable middle-aged yellow dwarf, has been burning for about 4.6 billion years and has approximately 5 billion years remaining. When it eventually exhausts its hydrogen, it will swell into a red giant, expanding until its outer layers engulf Mercury, Venus, and quite possibly Earth. Then it will shed those outer layers into a beautiful expanding cloud called a planetary nebula. What remains at the center will be a white dwarf, a dense, hot, slowly cooling remnant about the size of Earth, packed with roughly half the original stellar mass. White dwarfs do not fuse elements. They simply radiate stored heat, cooling over billions of years like an ember that receives no fresh fuel. Eventually, timescales tens of trillions of years, a white dwarf cools to the point where it emits, essentially, no light at all. Astronomers call this hypothetical endpoint a black dwarf. No black dwarfs exist yet. The universe has not been around long enough for any white dwarf to cool that completely. But the first of them will eventually form, representing the final fate of stars in the Sun's mass range. Below the Sun's mass range lies a threshold that is crucial to our story. The boundary below which stars never become red giants, never shed planetary nebulae, never leave white dwarfs behind. Stars below roughly 0.8 solar masses are expected to simply remain on what astronomers call the main sequence, burning hydrogen quietly and steadily for their entire theoretical lifespan, which for the smallest of them exceeds the current age of the universe by more than 1,000-fold. These are the red dwarfs, and they will inherit the universe. The sky, seen from Earth, contains no shortage of dramatic and brilliant objects. Sirius blazes at the top of the brightness rankings. A star twice the Sun's mass, burning hot and white. Betelgeuse glows red-orange at Orion's shoulder, a supergiant so enormous that if placed at the Sun's position, it would swallow everything out to Jupiter. The brightest stars in Earth's night sky are, almost without exception, rare and exceptional objects, not representatives of the typical stellar population, but outliers made visible by their extraordinary luminosity. The truth of the galaxy is much quieter than the sky suggests. Approximately 70 to 75% of all stars in the Milky Way are red dwarfs. They are the overwhelming majority. The galaxy is not a gallery of brilliant supergiants and blazing blue-white stars. It is, in the main, a collection of small, dim, cool, long-lived embers, most of them invisible to the naked eye from Earth. The largest red dwarfs are roughly half the mass of the Sun. The smallest are just barely above the minimum mass required to sustain hydrogen fusion, about 7.5% of the Sun's mass. Below that threshold lies a class of objects called brown dwarfs, which collapse under gravity and heat up, but never quite achieve the core temperatures required to sustain steady fusion. Brown dwarfs glow faintly for a while from the heat of gravitational contraction, but they are not stars in the true sense. Red dwarfs occupy a peculiar position in the universe. By almost every measure, they are unremarkable. They are small. They are dim. Faintest red dwarfs emit only a tiny fraction of the Sun's luminosity, so faint that they would be invisible to the naked eye even from a distance of just a few light years. They are cool, with surface temperatures often below 4,000 Kelvin. The Sun, by comparison, burns at nearly 5,800 Kelvin. They burn so slowly and at such low temperatures that they never build up the internal layering that leads medium mass stars like the Sun through their eventual red giant phase. They simply burn steadily and reliably for an almost inconceivable span of time. The smallest red dwarf stars that exist today, if they have existed since the early universe, will not exhaust their hydrogen fuel for another 10 trillion years. 10 trillion. The number is almost impossible to relate to human experience. But perhaps this helps. The light from the most distant galaxies we can observe left its source when the universe was only a few 100 million years old. Every human civilization, every species that has ever lived on Earth, every geological era, the entire history of multicellular life, the formation of our solar system, all of it has occurred within the first 0.1% of a red dwarf's lifespan. They are not just the longest-lived stars. They are so long-lived that the concept of aging requires a different framework to apply to them. But there is one more reason red dwarfs are different in a way that matters to our story. Unlike stars in the Sun's mass range, red dwarfs are fully convective. This means the entire interior of the star is constantly circulating. Hot material rising from the core, cooler material sinking back down, which continuously replenishes the core with fresh hydrogen. A red dwarf does not accumulate an ash of spent fuel the way a larger star does. It has access to essentially its entire hydrogen reserve from center to surface throughout its life. This matters enormously for their longevity. A star that can access all of its hydrogen lives dramatically longer than one that exhausts the fuel in its core first and then struggles to burn the remaining reserves. Red dwarfs are, in a very real sense, maximally efficient. They waste almost nothing, and they will burn long after everything else has gone dark. As the universe ages, the silence begins with the largest and brightest. Within the first few billion years of cosmic history, the most massive stars, those with dozens of times the Sun's mass, have already died. They flared brilliantly, collapsed violently, and scattered their enriched debris across the interstellar medium. Their supernovae seeded subsequent generations of stars with carbon, oxygen, and all the elements that make complex chemistry possible. They were catastrophic and essential, but they are gone. As we move forward through cosmic time, past our current era, past 5 billion years from now, when the Sun itself will begin its final transformation. The remaining stellar population becomes increasingly dominated by smaller, quieter, redder stars. The universe's light becomes less blue, less brilliant. There are fewer supernovae. The energetic events that make galaxies glow with ultraviolet light become rarer. The night sky, observed from a hypothetical vantage point in the far future, would look perceptibly different from what we see today. Redder, quieter, with the most dramatic and brilliant objects already gone. This is not a sudden transformation. It is a gradual dimming, stretched across billions of years, noticeable only if you could compare observations separated by vast stretches of time. By roughly 1 trillion years from now, 100 times the current age of the universe, star formation will have essentially ceased. The gas that once fed new stellar ignitions has been consumed, expelled, or heated beyond usefulness. The universe will still be filled with stars, but they will all be old. Stars that formed in the distant past, still burning through their hydrogen reserves, with no new stars being born to replace them. It is a universe of survivors, not of new arrivals. During this long era, which cosmologists sometimes call the stelliferous era, the era of stars, the universe continues to support warmth and light. Planets around red dwarfs continue to orbit. Energy still flows. The conditions that allow chemistry to occur, that allow temperatures above absolute zero to exist on planetary surfaces, remain intact for some of those worlds. Whether life persists in this era, whether some form of biology could sustain itself around a dim, slow-burning red dwarf for trillions of years, is a question that science can frame but cannot yet answer. What seems clear is that the conditions required for some form of complexity to exist, energy, chemical gradients, liquid environments, remain at least plausible for much of this era. But the stars are dying. One by one, in the order their mass dictates, they are running out of fuel. The medium-mass stars, those near the Sun's mass, exhaust their hydrogen supply first within their stellar class, on timescales measured in billions to tens of billions of years. Then they go through their red giant phase, shed their outer layers, and leave white dwarfs behind. The slightly smaller ones, those perhaps 80% of the Sun's mass, take longer, but eventually follow the same path. And slowly, the red dwarfs remain. Not dramatically, not as the obvious winners of some cosmic endurance contest. They simply outlast everything else, burning their fuel so slowly that by the time a star twice the Sun's mass has completed its full life cycle, the smallest red dwarfs have barely begun. They are not racing, they are simply patient. Let us try to imagine one particular star, the last star that will ever shine in the universe. We cannot know exactly which star it will be. We cannot point to a specific object in the current catalogue of red dwarfs and say, that one. The processes that determine stellar lifespan involve not just initial mass, but the specific history of interactions with other objects, the precise rate of mass loss over time, the specific conditions in which the star formed. Some uncertainty is irreducible, but we know with reasonable confidence what kind of star it will be. A red dwarf of very low mass, perhaps 7 or 8% of the Sun's mass, just barely above the threshold at which hydrogen fusion becomes sustainable. Its surface temperature might be around 2,000 to 20,500 Kelvin, cooler than most lava flows, so cool that the star glows not white or yellow, but a deep, dark red, producing most of its light in infrared wavelengths rather than the visible spectrum. From a human perspective, it would be barely recognizable as a star. You could look at it from a relatively short distance, a few hundred kilometers, and not feel the intense heat that our sun radiates. Its light would be dim, reddish, almost melancholy in quality. You could stare at it without pain, but it would be burning, quietly, reliably burning. And in that burning, it would be doing what all stars do, converting hydrogen into helium, releasing energy, producing the faint warmth that, at the right distance, with the right conditions, could in principle sustain the chemistry of liquid water and complex molecules. Around this star, there may or may not be planets. Whether any of those planets still host anything resembling active chemistry or biology after trillions of years of stellar evolution is a question whose answer we cannot know. What we know is that the star will be burning in a universe otherwise dark, in a galaxy that has long since ceased producing new stellar fires, in a cosmos where the concept of a galaxy itself will have been altered almost beyond recognition by the gravitational dynamics of deep time. Because while we have been focused on stars, the large-scale structure of the universe has also been changing. Galaxies are not static structures. They are dynamic collections of hundreds of billions of stars, bound together by gravity, constantly evolving through encounters with each other, internal dynamics, and the slow march of stellar evolution. Over billions of years, galaxies merge. The Milky Way and the Andromeda Galaxy are currently approaching each other at roughly 110 kilometers per second and are expected to begin their collision in about 4.5 billion years. This will not be a sudden violent crash in the way the word collision suggests. The distances between individual stars are so vast that stars themselves rarely collide directly. What happens instead is a gravitational dance. The two galaxies interpenetrating, stars being flung into new orbits, tidal tails of material stretching across hundreds of thousands of light years, the overall structures distorting and eventually merging into a single, large elliptical galaxy. Astronomers sometimes call the expected result Milkomeda. Over longer timescales, tens of billions to trillions of years, galaxy clusters and groups continue their own gravitational evolution. Smaller galaxies fall into larger ones. The dark energy that is currently accelerating the expansion of the universe will at some point also determine the fate of large-scale structures. The precise details remain an active area of research, but the broad picture is of increasing isolation. Local gravitational systems bound together, drifting apart from each other as the universe expands between them. Eventually, by the time we reach the era of the last stars, our galaxy, or whatever remains of the merged structure that contains its descendants, will be an old elliptical galaxy, populated primarily by the dimmest and coolest red dwarfs, with the more massive stars already long dead, and their remnants in the form of white dwarfs, cooling slowly in the dark. The structure will still exist. Gravity still binds it. But the stellar population will be almost unrecognizable compared to the dynamic, multicolored, energetic galaxy we see today. And over even longer timescales, the dynamics of the galaxy itself will change in a more fundamental way. Stars, moving through the galaxy on their long orbits, occasionally pass close enough to each other to exchange gravitational energy. Over trillions of years, these encounters, each individually tiny in their effect, accumulate. Some stars gain energy from these interactions and drift outward, eventually being ejected from the galaxy entirely. Others lose energy and sink toward the center. This process, called two-body relaxation, very slowly erodes the galaxy from the outside in, with some fraction of the stellar population being flung into intergalactic space, while the rest gradually concentrates toward the galactic center. This matters for the last star. By the time we are approaching the final era of stellar burning, the galaxy may be a much more diffuse and scattered structure than it is today. Stars that were once part of dense stellar neighborhoods may have drifted far apart. The last red dwarfs may be burning in relative isolation, separated by distances so vast that even the concept of a galaxy begins to break down. The last star in the universe may be the last star, not just chronologically, but literally alone. The only burning object in a vast, dark, cold, expanding universe. Time, at this point in our journey, requires yet another recalibration. We have moved through what feels like an enormous span. From the Big Bang through the Dark Ages, through the peak of star formation, through the billions of years of our current era, through the slow decline of massive stars, and the eventual death of stars like the Sun, we have arrived at a future so remote that the entire history of the universe so far accounts for less than 1% of what has elapsed. And yet the last star is still burning. The reason is that last star's extraordinary patience. A red dwarf of minimum mass burning at its lowest sustainable rate can shine for roughly 10 to 15 trillion years. Some theoretical models extend this further to 20 trillion, even 100 trillion years, depending on the precise assumptions about stellar physics at very low masses and very long timescales. Let us sit with 100 trillion years. If you were to count to 100 trillion, one number per second, without pause, without sleep, it would take more than 3 million years, more than twice as long as our species has existed. Every second of counting would represent an entire year of cosmic time. And you would still be counting. During those 100 trillion years, the universe will look almost nothing like the cosmos we inhabit today. The cosmic microwave background radiation, the faint afterglow of the Big Bang, still detectable by our instruments as a uniform glow of microwave radiation, will have redshifted to such long wavelengths that it will be essentially undetectable by any instrument we can imagine. The temperature of the universe will be extraordinarily close to absolute zero. The expansion of the universe will have pushed almost all other galaxies, even those in our local group, so far away that their light will never reach whatever observational platform might exist. Here, the universe will be dark, almost entirely dark, and cold, and quiet in a way that the word quiet was not designed to describe. Except for the red dwarfs, still burning, still converting hydrogen to helium, still, in their small and modest way, maintaining the tiny islands of warmth that represent the last remnants of what we might recognize as an active, energetic universe. They are not aware of their own significance, of course. Stars are not aware of anything. They are simply obeying physics, but there is something almost moving about the image. These small, dim, patient fires, burning in a universe that has otherwise grown cold and dark, simply because they have enough fuel, and the physics of hydrogen fusion doesn't know when to stop. And one by one, even they eventually exhaust their supply. When a red dwarf finally runs out of hydrogen, what happens is quiet and strange. Unlike stars in the sun's mass range, red dwarfs do not swell into red giants. They lack the internal mass and the associated gravitational and pressure dynamics that drive larger stars through that expansion. Instead, as their hydrogen supply dwindles, they undergo a different transformation. As the hydrogen fuel depletes, the fusion rate decreases. The balance between gravity and outward pressure shifts gradually. The star contracts somewhat. The remaining hydrogen, increasingly mixed with the helium that has accumulated from billions of years of fusion, burns at a changing rate. Some models suggest that in their final stages, low-mass red dwarfs may actually brighten somewhat and become bluer before their fuel is finally spent. A brief, almost defiant flare before the end. They may transition through what is called a blue dwarf phase, something that does not exist anywhere in the current universe, precisely because no red dwarf has lived long enough to reach this stage. Eventually, the fusion can no longer be sustained. The energy output drops. The outward pressure that has counterbalanced gravity for trillions of years finally loses its battle. The star begins to collapse, not explosively, as a massive star would, but slowly, cooling as it shrinks. What remains is a white dwarf, a dense, cooling sphere of helium, approximately the size of Earth, glowing faintly from residual heat. Over time, measured again in trillions of years, even that faint glow will fade. But the last red dwarf to undergo this process will be the final one. When it collapses into its white dwarf remnant, the last light produced by nuclear fusion anywhere in the universe will be extinguished. There will be no more stars, no more starlight. The universe will enter an era without fire. That moment, whenever it occurs, whatever specific star produces it, in whatever remote corner of whatever remains of our local galactic structure, is the moment we began this journey trying to understand the last star. And what we find when we try to imagine it is not a blaze of cosmic glory. It is not a magnificent final supernova visible across the universe. It is something far quieter and in its own way far more remarkable. It is a small, dim, reddish star burning slowly in the dark and then cooling. When the last red dwarf collapses into its white dwarf remnant, the universe does not end. This is perhaps the most important thing to understand about the death of the last star. The universe does not care. It continues. The laws of physics do not pause, do not mourn, do not register the event as a threshold. Matter still exists. Energy still exists, though increasingly diffuse and cold. Space still expands. Time still passes. What ends is not the universe. What ends is the era in which the universe contained fire. And what follows is something that human language was genuinely not constructed to describe, because no human mind has ever needed to think seriously about it until the last century or so of scientific inquiry. What follows is an era so long, so dark, so cold, and so structurally different from everything that came before it, that calling it the future feels almost misleading. It is more accurate to say it is a different kind of universe, one that operates by the same physical laws, but whose contents and conditions differ so dramatically from the universe. We know that most of the vocabulary we use for cosmology would need to be retired or redefined. Astronomers and physicists who study this future have given this era a name: the degenerate era. It begins when the last star dies and ends, if ends is even the right word, many trillions of years later, when the remnants of dead stars themselves begin to fade and decay. During the degenerate era, The universe is populated not by burning stars, but by their cooling corpses. White dwarfs, neutron stars, and black holes. These objects still exist, still occupy space, still interact gravitationally. But they produce no new energy from nuclear fusion. They are coasting on stored heat, structural integrity, and the faint processes of decay. To understand this era, and to understand why it matters for the story of the last star, we need to understand what these remnants actually are, and what physics does to them over unimaginable stretches of time. A white dwarf is one of the most extraordinary objects in the known universe, and also one of the most common endpoints of stellar evolution. When a star like the Sun exhausts its hydrogen and sheds its outer layers, what remains at the center is a sphere roughly the size of Earth, but containing roughly half the original star's mass. The density is almost incomprehensible. A teaspoon of white dwarf material would weigh somewhere in the range of 5 to 15 tons on Earth's surface. The material is so compressed that the electrons within it can no longer occupy the energy states they would in normal matter. They are forced into a quantum mechanical configuration called electron degeneracy, a state in which the Pauli exclusion principle, one of the fundamental rules of quantum mechanics, prevents further compression by generating a pressure that is entirely unrelated to temperature. This is why white dwarfs do not immediately collapse into something smaller. They are held up not by fusion, not by thermal pressure, but by a purely quantum mechanical effect. The refusal of electrons to occupy the same quantum state simultaneously. It is physics at its most fundamental, holding a stellar remnant together by a rule that operates at the level of individual particles. But white dwarfs are hot when they form, very hot. Newly formed white dwarfs can have surface temperatures of 100,000 degrees Kelvin or more. And over time, without any internal energy source to sustain that heat, they cool. They radiate their stored thermal energy slowly into space. They dim. They fade. The question of how long this cooling takes is one of the reasons we know that the universe has not yet been around long enough for any white dwarf to cool completely. The oldest white dwarfs we can observe, the remnants of the first stars to have died in the universe, still have surface temperatures of thousands of degrees Kelvin. They have been cooling for billions of years and are still warm. The theoretical endpoint of a completely cooled white dwarf is what physicists call a black dwarf. A cold, dark, inert sphere of crystallized carbon and oxygen, roughly the size of Earth, radiating essentially no light and producing no energy. It would be invisible, undetectable except by gravitational effects. A planet-sized diamond of stellar ash drifting through a dark universe. No black dwarfs exist yet. The universe is too young, but in the degenerate era, as the trillions of years accumulate, white dwarfs will slowly cool toward that endpoint. The universe will fill, gradually, with these dark remnants, and the darkness will deepen. There is, however, one more process that could affect white dwarfs over extremely long timescales. A process whose existence remains theoretical, but whose physics is well-founded. It is called proton decay. The standard model of particle physics, and most of its extensions, predict that protons, the fundamental building blocks of atomic nuclei, are not perfectly stable. They should, over extraordinary spans of time, occasionally decay into lighter particles. The predicted time scale for proton decay, depending on the theoretical model, ranges from around 10 to the 33rd power years to 10 to the 45th power years and beyond, to give you a sense of what those numbers mean. 10 to the 33rd power years is a trillion times a billion years. It is a number so large that writing it out in standard notation requires 33 digits if proton decay occurs at the lower end of theoretical predictions. White dwarfs and neutron stars would not simply cool into dark permanent remnants. They would gradually dissolve, their constituent protons decaying away, releasing small amounts of energy in the process, until the matter that makes up stellar remnants is itself converted into lighter particles and radiation. The universe would, eventually, run out of ordinary matter entirely. Whether proton decay actually occurs remains one of the open experimental questions in physics. Experiments have been running for decades, looking for the signature of a proton decay event, and none has been detected. This either means proton decay is extremely rare, consistent with the longer theoretical timescales, or that it does not occur at all, in which case the black dwarfs formed from cooled white dwarfs may persist essentially forever, or until some other physical process acts on them. Either way, the universe in the degenerate era is a place of extraordinary patience and extraordinary darkness, punctuated only by the occasional faint glow of still cooling stellar remnants and the even fainter processes of quantum mechanical decay. But there is one category of stellar remnant that operates by entirely different rules, and it will outlast everything else, even the white dwarfs, even the neutron stars, by an almost incomprehensible margin. Black holes are not, as they are sometimes portrayed, simply regions where gravity is very strong. They are something more fundamental and more strange than that description suggests. A black hole is a region of space-time in which the curvature of space, caused by the concentration of mass or energy at its center, becomes so extreme that not even light can escape. The boundary of this region is called the event horizon. Cross it, and the laws of physics as we understand them make return impossible. Not difficult, impossible. The geometry of space-time inside an event horizon is such that all possible paths through space and time lead toward the center. There is no direction that points outward. To escape a black hole, you would need to travel faster than light, and nothing with mass can do that. Black holes form primarily in two ways. The most dramatic is the core collapse of a massive star. When the iron core of a star, with perhaps 20 or more solar masses, collapses in a supernova, if the remaining core mass exceeds a certain threshold, not even the quantum mechanical pressure that supports neutron stars can prevent further collapse. The core becomes a black hole, the most massive stellar remnant possible. The second way involves the merging of existing compact objects, neutron stars and black holes merging over time through gravitational wave emission, with the merged object collapsing into a black hole if its mass exceeds the neutron star stability limit. And then there are the supermassive black holes at the centers of galaxies. Objects containing millions to billions of solar masses whose origin involves a combination of early universe processes and billions of years of merging and accretion. Our own Milky Way harbors one called Sagittarius A, with a mass of approximately 4 million suns. In the present universe, black holes are often thought of as voracious, consuming material that falls within their gravitational reach, occasionally blazing as quasars or active galactic nuclei when large amounts of material fall inward at once. But in the far future, in the cold darkness of the degenerate era, there is very little material left to consume. Stellar remnants and diffuse gas and dark matter still exist, but most of it is not falling into black holes. The universe has expanded and cooled too thoroughly. The supply of infalling material has largely been exhausted. Black holes, in the degenerate era, are patient. They sit in the dark, their immense gravity extending outward, slowly accumulating any material that wanders close enough. Through the process of dynamical friction and gravitational interactions, they gradually incorporate the stellar remnants that drift into their vicinity. The supermassive black holes at galactic centers grow slowly, consuming the cooling white dwarfs and neutron stars that eventually spiral inward. But here is the truly remarkable thing about black holes over deep cosmic time. They evaporate. In 1974, the physicist Stephen Hawking made a discovery so surprising that even he reportedly found it difficult to accept at first. He showed, through a combination of general relativity and quantum field theory, that black holes are not perfectly black. They emit radiation. The mechanism is subtle and worth understanding because it determines the ultimate fate of the last gravitational structures in the universe. Quantum mechanics tells us that empty space is not truly empty. At the smallest scales, the vacuum is a seething, probabilistic environment in which pairs of virtual particles, a particle and its antiparticle, continuously emerge from nothing and annihilate back into nothing, existing for a span of time so brief that quantum uncertainty allows it. This process of virtual pair production occurs everywhere, all the time, and under normal circumstances produces no observable effect because the pairs always annihilate before they can be detected. Near the event horizon of a black hole, however, something different can happen. A pair of virtual particles appears just at the horizon. One particle falls inward, inside the event horizon. The other particle, finding itself on the outside, can no longer annihilate with its partner. That partner is now inside the black hole and inaccessible. The outside particle escapes into space as real radiation. The black hole, to conserve energy, must lose a small amount of mass equivalent to the energy of the escaped particle. The black hole radiates, very, very slowly, very, very faintly. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Larger black holes radiate at lower temperatures. A stellar mass black hole of a few solar masses radiates at a temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero, utterly undetectable against the background radiation of the current universe, which is still at about 2.7 Kelvin. But in the far future, when the universe has cooled below a Hawking temperature of these black holes, they will be the warmest things in existence, and they will slowly, inexorably lose mass. As a black hole loses mass through Hawking radiation, it gets smaller. As it gets smaller, its Hawking temperature rises. As the temperature rises, it radiates more intensely. This creates a feedback process, slow at first, enormously accelerated near the end. That ultimately results in the complete evaporation of the black hole in a brief burst of high-energy radiation. The timescale for this evaporation depends on mass. A stellar mass black hole of a few solar masses takes approximately 10 to the 67th power years to evaporate. That number written out has 67 digits. A supermassive black hole of 1 billion solar masses takes approximately 10 to the 97th power years. An extreme case, A black hole of 100 billion solar masses might take 10 to the 105th power years. These numbers are so large that they make the age of the universe, the entire stellar era, the entire history of everything we have called cosmic history, look like a rounding error. The time required for the largest black holes to evaporate is so vast that the phrase "a long time" is genuinely inadequate. No analogy drawn from human experience or even from astronomical observation can make these timescales feel real. They can only be stated and sat with. But eventually, at whatever point corresponds to the evaporation of the last and most massive black hole in the universe, even this process ends. The black hole releases its final burst of Hawking radiation, and the last concentrated mass energy in the universe disperses into elementary particles and photons. And then there is nothing left that could, in any meaningful sense, be called a structure. After the last black hole evaporates, what remains? Physicists who have worked through the mathematics of the far future. Researchers like Freeman Dyson, Fred Adams, Gregory Laughlin, and others call what follows the Dark Era, or sometimes, with less poetry but more accuracy, simply the final state. The contents of the universe at this point would be extraordinarily sparse. Photons, particles of light, produced by the evaporation of black holes and the decay of particles across the preceding eras, now stretched to enormous wavelengths by the expansion of the universe. Electrons and positrons drifting through space, separated by distances so vast that they almost never encounter each other, but occasionally annihilating when they do, producing more long-wavelength photons, neutrinos, moving at nearly the speed of light but carrying so little energy that they barely interact with anything. And depending on whether proton decay occurs, either the remnants of matter in the form of slowly decaying protons, or the products of that decay dispersed into lighter particles. The temperature of the universe approaches, but asymptotically, absolute zero, never quite reaching it, because the occasional particle interaction and the background of long wavelength photons maintain an infinitesimal temperature above the minimum. But for any practical description, the universe in the Dark Era is cold in a way that no laboratory on Earth has ever achieved. Cold in a way that would freeze any chemical process, cold in a way that makes the phrase cold vacuum of space, already describing a temperature that would kill a human in moments, seem positively warm and welcoming by comparison. There is no fire, there are no stars, there are no white dwarfs, no neutron stars, no black holes. There is no structure in the universe at a scale larger than an occasional wandering particle. There is only expansion. Space continuing to grow as dark energy continues to drive the universe outward. And within that expanding space, the final sparse inventory of the universe's contents. Photons, electrons, neutrinos, and perhaps the last slow products of particle decay, drifting further and further apart, interacting less and less frequently. This is the universe's final state, as best as physics can currently describe it. Not a dramatic end, not a collapse, not a conflagration. A slow, nearly silent dispersal into maximum entropy. The thermodynamic endpoint that physicists call heat death. Not because the universe becomes hot, but because all the temperature gradients that allow energy to do useful work have been eliminated. The universe reaches a state of uniform, maximum disorder, from which no further change of any organized kind is possible. And it stays that way, presumably forever. Though forever and stays and even way become philosophically fraught terms when applied to a state in which nothing ever changes, where time itself, which we measure by change, has become essentially meaningless. There is a question buried inside all of this that most scientific accounts of the far future do not address directly. But that may be the most quietly profound question of all. Does the universe, in any meaningful sense, remember that it once contained stars? At first, this sounds like a philosophical question rather than a physical one. But it has a physical answer, and the answer is genuinely unsettling. Memory, in the physical sense, requires structure. Information is stored in the arrangement of matter, in the patterns of atoms in a crystal, in the configuration of molecules in a strand of DNA, in the precise positions of components in a computer's memory. The persistence of information over time requires that the physical structure encoding it be maintained against the tendency of entropy to disorder everything. In the far future, the structures that could encode information about the universe's history are systematically destroyed. Stars are gone. The planets that once orbited them are gone, absorbed into stellar remnants, ejected into intergalactic space by gravitational dynamics, or simply dissolved if proton decay occurs. The civilizations that might have recorded the history of the stellar era are gone. The light that was emitted by stars is still traveling. Photons last essentially forever in the absence of absorption. But it has been stretched by the expansion of the universe to wavelengths so long that they carry almost no energy and encode almost no information in any recoverable form. The universe, in the dark era, does not remember that it once burned with stars. Not because the information was actively erased, but because the structures that could preserve it have been dismantled, particle by particle, over an incomprehensible span of time. Entropy, the tendency of closed systems to move toward maximum disorder, is not a force that acts suddenly. It is a tendency that acts relentlessly across every scale of time and matter. And given enough time, which the dark era has in surplus, it accomplishes everything. There is something that feels almost like loss in this, though the universe itself is not capable of feeling anything. The billions of years during which stars burned, during which planets formed and were warmed, during which at least one world produced observers curious enough to ask these questions. All of that will leave no lasting trace in the physical universe. The record will be erased not by any catastrophe, but simply by the passage of enough time. But here is a reframing worth sitting with. The fact that the record will eventually be erased does not mean the record does not exist now. The information about the stellar era exists in this moment, in the light that still travels across the universe, in the elements forged in stellar cores that now make up planets and organisms, in the civilizations and curiosities and questions that stars made possible. The impermanence is real, but so is the existence. And there is something philosophically significant about the fact that, as far as we know, we are among the first observers in the universe to understand this story. We exist at a point in cosmic history where the universe is still young enough to contain stars, still rich enough in energy for biology to function, and old enough that the universe's history can be traced and its future projected. We occupy, in some sense, a privileged moment. Not privileged in the sense of being cosmically important, but privileged in the sense of being positioned to witness a great story in progress. The stars that burn today will not burn forever, but they burn now, and we can see them. Before we arrive at the last star itself, there is one more question worth exploring. A question that science can begin to frame, but cannot yet definitively answer. Could life exist in the era of the red dwarfs? This is not as remote or speculative as it might initially seem. We are, as we have already discussed, living in the declining phase of star formation. The red dwarfs that dominate the future stellar era are already here, already numerous, already surrounded in some cases by planets. The question of whether red dwarf planets can support life is one of the most actively studied questions in contemporary exoplanet research. The challenges are significant. Red dwarfs, for all their longevity, are not placid hosts for planetary biology. In their early years, which for a red dwarf might still mean the first billion years or so, they are prone to intense stellar flaring activity. These flares release enormous bursts of ultraviolet and X-ray radiation, a planet in the habitable zone of a red dwarf. The region where liquid water could theoretically exist on the surface is much closer to the star than Earth is to the Sun, because red dwarfs are so dim that proximity, combined with the flaring activity, could strip away planetary atmospheres or subject any surface life to radiation levels that make biology difficult. But there is a counter-argument. Life on Earth began, as best we can determine, within the first billion years of Earth's history, during precisely the period when our own Sun was also more active and variable than it is today. Life does not require a perfectly calm stellar host. It requires liquid water, chemical complexity, and an energy source. Red dwarfs, for all their early turbulence, eventually settle into long periods of relative stability. And their extraordinary longevity means that even if it took several billion years for life to gain a foothold around a red dwarf planet, there would still be trillions of years remaining for that life to evolve. The timescales available around a long-lived red dwarf, if you will forgive the construction, the timescales available around a long-lived red dwarf enormously exceed anything Earth has experienced. Life on Earth has had roughly 3.8 billion years to progress from simple chemistry to complex multicellular organisms, intelligence, civilization, and the capacity to observe the universe. That is a remarkable trajectory. But a civilization arising around a red dwarf and surviving for even a fraction of the star's multi-trillion-year lifespan would have access to an evolutionary and technological timeline that makes our entire history look like a prelude. What might such a civilization understand? What questions might it have answered? What observations might it have made of a universe still containing stars, from a temporal vantage point that we can barely imagine? We do not know. We cannot know. Any civilization that might exist around a distant red dwarf is inaccessible to us, separated not just by space, but by time. We are a young civilization around a middle-aged star, looking out at a universe still in its stellar prime, able to project the future, but unable to observe it directly. But the question of whether the stellar twilight era harbors life is not merely speculative. It is a genuine scientific question, with implications for how we understand the distribution and persistence of complexity in the universe. If life can arise and survive in the cool, slow-burning environs of a red dwarf system, then the overwhelming majority of life that will ever exist in this universe has not yet arisen. The stellar era has barely begun by the measure of red dwarf timescales, and life's story in this universe is still near its opening pages. That possibility however uncertain, is one of the most quietly extraordinary things about the universe we inhabit. There will be a moment, somewhere between 1 trillion and 100 trillion years from now, at a point in the universe's timeline so remote that there is no human reference for it, when the last new star forms. Not the last star that will ever burn, but the last star that will ever ignite. The last instance of raw gas or infalling material accumulating enough mass to initiate hydrogen fusion for the first time. This last ignition will be a quiet event. The gas available for star formation will, by this point, be extraordinarily scarce. The great stellar nurseries, the giant molecular clouds that dot our galaxy today, the regions where thousands of new stars are born, simultaneously in cascades of gravitational collapse and radiative feedback. Those structures are products of a universe still rich in cold gas and energetic enough to drive the complex dynamics of star formation. They will have ceased to exist long before the last ignition. What remains near the end of the star-forming era will be the occasional small accumulation of gas, perhaps material ejected from a stellar interaction, or the diffuse material that still lingers between stellar remnants after most of the galaxy's gas supply has been consumed. If enough of this material accumulates in a small enough region, gravity can still initiate the collapse that leads to fusion. The last such event will be small. The last new star to ignite in the universe will almost certainly be a red dwarf, the only type of star that can form from a small enough gas reservoir to be the last one available. It will ignite without ceremony. There will be no observers, no explosion, no brilliant flash, no signal traveling across the universe to announce the event, just the quiet beginning of nuclear fusion in a small ball of hydrogen, in the darkness of a universe that has largely already moved on. And then it will burn. For trillions of years, it will burn. That last ignited star may also be the last star to die, or it may not. There may be red dwarfs currently burning, already old, whose extreme longevity means they outlast even a star that ignites later but with slightly more mass. The precise ordering of the last star events, last ignition, last burning, last death, is not something we can determine from our current observational position. But the broad sequence is clear. The last stars will be small and red, and their deaths will be quiet. We have traveled an extraordinary distance from the present moment, across trillions of years of cosmic time, through the death of stars and the evaporation of black holes, and the ultimate dispersal of matter into a cold, dark, structureless expanse. It is worth returning now to the night sky. Find a clear night. Step outside. Let your eyes adjust to the darkness for 15 or 20 minutes. The stars will begin to appear. First the brightest ones, then more and more as your pupils dilate and your visual cells adapt. On a sufficiently dark night, away from city lights, the Milky Way itself becomes visible. A faint, diffuse band of light crossing the sky. The collective glow of hundreds of billions of stars, most of them too distant to resolve individually. Every point of light you see is a nuclear furnace. Everyone is, at this moment, converting hydrogen into helium at an extraordinary rate, producing in the process the light that has traveled across space to reach your eyes. Some of that light left its source before Earth existed. Some left before our solar system had formed. Some is coming from stars that no longer exist, stars that died while their light was still in transit, so that what you see is a kind of message from an object that has already burned out. The night sky is not a static scene. It is a snapshot of an ongoing process, the middle of the universe's great stellar era, now clearly past its peak, but still abundant with fire. Every star you see is burning through its fuel supply, moving toward the endpoint that each one is already determined by physics to eventually reach. And among those stars, scattered across the sky in numbers too faint for you to see individually without a telescope, are the red dwarfs, the quiet, dim, patient ones, the inheritors, the ones whose light is too faint for the naked eye, but whose presence fills the galaxy in enormous numbers. Some of them are burning tonight with light that will still be burning 100 times longer than the sun has yet existed. Some of them may already have planets. Some of those planets may already be warm. The night sky tonight contains both the recent past and the distant future simultaneously. The brilliant stars, Sirius, Rigel, Betelgeuse, Canopus, are the ones nearest their endings, cosmically speaking. The ones that will last are the ones you cannot easily see. There is something quietly significant about that inversion. One of the deepest insights in all of science is that the universe, at the largest scales, operates under a principle of irreversibility. You can stir cream into coffee, but you cannot unstir it. You can break an egg, but you cannot unbreak it. The laws of physics, at the level of individual particles, are almost entirely reversible in time. A film of particles colliding would look equally valid, played backward as forward. But at the level of large collections of particles, this time reversal symmetry breaks down. The increase of entropy, the tendency toward disorder, points time in one direction. And that direction is the same direction in which stars are born and die, in which the universe expands and cools. The stars are a chapter in a story that only moves in one direction. The hydrogen that formed the first stars came from the Big Bang, a single, ancient event that produced the initial conditions from which all subsequent structure emerged. That hydrogen cannot be reclaimed once it has been fused into helium. The helium cannot be unfused back into hydrogen. The iron in dead stellar cores cannot spontaneously reassemble into fusion-ready fuel. The entropy that increases with every stellar ignition, every nuclear reaction, every photon radiated into space, it cannot decrease. This means the stellar era has a definite endpoint. Not a theoretical endpoint that might be averted by some fortunate turn of events, but a physical endpoint written into the laws of thermodynamics. The universe's hydrogen supply is finite. The conditions that allow new hydrogen to be gathered and fused are becoming rarer with each passing era. The last star is not a possibility. It is a certainty. Physics demands it, and this is, in its own way, one of the most remarkable things about living in the universe at this particular moment. We are burning hydrogen. Right now, the sun is converting 4 million tons of mass into energy every single second. It has been doing this for 4.6 billion years. The hydrogen it is burning today will never be hydrogen again. There is an irreversibility to the stars that gives them a quality almost like preciousness. Not in the sense that they should be preserved, because they cannot be, but in the sense that their burning represents something genuine and unrepeatable. The light reaching Earth from the sun today is the product of fusion that occurred 8 minutes ago. That light will never exist in quite that form again. The sun that burns today is not the sun that burned yesterday, and both are lost, in a precise physical sense, to the permanent past. This is not cause for grief. It is simply the nature of things. But Understanding it changes, in a subtle way, how the stars above feel on a clear night. Let us return one final time to the last star itself, and try to know it as well as physics allows. It is, most likely, a red dwarf, with a mass somewhere between 7 and 15% of the Sun's mass. Its surface temperature is low enough that most of its energy is radiated in infrared light. Warmth rather than visible glow. If you could place it in our solar system where the Sun now sits, Earth would be dark and frozen. The star too dim to provide meaningful warmth at that distance. A planet in its habitable zone would need to orbit much closer, within a distance that would make a year last perhaps 10 to 30 Earth days. Its interior is fully convective. The entire body of the star circulates slowly, like a vast, extremely slow-motion pot of water on the edge of simmering. Hot plasma from the nuclear burning core rises to the surface, radiates a small amount of energy, cools slightly, and sinks back down. This circulation continuously refreshes the fuel available for fusion and keeps the star burning uniformly throughout its volume, unlike the layered interiors of larger stars. It has been burning for a long time. How long depends on when it formed. But given the depletion of star-forming gas in the late stellar era, it may be one of the last stars to have formed, perhaps ignited in the few trillion years before the last new star formation event. Or it may be one of the very first red dwarfs, still burning, after having ignited early in the universe's history, and simply possessing a small enough mass that its fuel supply lasts incomprehensibly longer than everything around it. Either way, by the time it is the last star, it has been alone in its burning for a very long time. The more massive stars died first, billions of years ago, then trillions of years ago. The medium-mass stars followed, leaving their white dwarfs behind. The slightly more massive red dwarfs exhausted their fuel earlier. One by one, the stellar population has thinned, and the last star has watched. If stars could watch, the universe grow quiet around it. By the time it is truly the last one, it exists in a universe so different from the one in which it formed, that almost nothing would be recognizable. The galaxies have merged and diffused. The white dwarfs that were once its neighbors have cooled to near absolute zero, invisible dark spheres drifting on vast orbits. The cosmic microwave background has redshifted to wavelengths kilometers long, carrying no useful energy. The universe's temperature is so close to absolute zero that even the concept of heat, the random motion of particles, is barely meaningful. The last star burns on. Its fusion rate is exquisitely slow. The energy it produces per unit volume is tiny compared to the Sun. If you could stand on a planet orbiting it at the right distance, you would feel warmth, gentle, persistent, red-shifted warmth, but nothing like the fierce brightness of our own Sun on a clear day. The star's light would be dim and red, falling on whatever surface surrounded it with the quality of a very deep twilight that never fully becomes night. And then the hydrogen runs out. Not all at once. The fusion rate has been gradually declining for millions of years before the end. As the remaining fuel grows thinner and the conditions for sustaining fusion become marginally less favorable, there is no dramatic moment of cessation. The star gradually dims, its temperature falls, the energy output decreases, the equilibrium between fusion pressure and gravity shifts slowly toward gravity's advantage. The star contracts. It warms slightly as it shrinks. Gravitational potential energy converting to heat, which briefly sustains a slightly increased luminosity. Then the contraction slows as electron degeneracy pressure takes over. The star settles into its final configuration, a white dwarf, small, dense, warm, and no longer fusing. The last light produced by nuclear fusion in the universe is not a blaze. It is the final glow of a dimming red star, contracting to the size of a planet. Its surface cooling from red to deeper red to infrared to nothing. The universe's last stellar fire goes out. The darkness that follows the death of the last star is unlike any darkness that exists in the current universe. Every darkness we know is partial. A dark room still has air, still has warmth, still has the faint infrared glow of the objects within it. A dark night sky is pierced by starlight, the darkest place on Earth, the darkest place accessible to human experience. Still contains photons, still contains the cosmic microwave background, still contains the faint emissions of distant galaxies. We have never experienced true darkness, in the sense of an environment in which there is no light at all, and in which there is no source of light within any accessible distance. The universe after the last star dies approaches that condition. Not immediately. The universe is still filled with the light from the last star's death. The photons emitted as it cooled from a white dwarf. But those photons travel outward and away. The universe expands, the wavelengths stretch. The energy density drops. Over millions, and then billions, and then trillions of years, the photon bath grows thinner, and its wavelengths grow longer. The black holes remain for a time, immensely long. They do not provide visible light, but the Hawking radiation they emit, extraordinary faint, long wavelength, means that for as long as even the smallest black hole survives, there is technically radiation in the universe. A physicist who could detect it would find in the Hawking radiation of a stellar black hole a temperature of a few tens of nanokelvins. Not darkness, technically, but for any practical biological or chemical purpose. For any purpose that relates to how we experience warmth and light. Effectively darkness. After the last black hole evaporates, the remaining radiation is the legacy of all those evaporations. Long wavelength photons spreading through an expanding universe. They will persist. Photons, in the absence of matter to absorb them, travel indefinitely. But the universe's expansion stretches their wavelengths continuously, diminishing their energy, given enough time. And the dark era has time in quantities that make every prior timescale seem trivial. Even these photons will carry so little energy that they cannot, in any meaningful sense, be said to illuminate anything. There is a poetic and physically accurate statement to be made here. The universe, in its final state, is not dark in the way a room is dark when the lights are off. It is dark in the way that a room would be dark if the concept of light had never existed, and the room was the entire universe. The distinction is not one of degree, it is one of kind. After a journey through this much darkness, it is worth asking, what does the story of the last star tell us about the era we currently inhabit? The stellar era, the period during which nuclear fusion produces starlight somewhere in the universe, spans roughly from a few 100 million years after the Big Bang to somewhere between 1 trillion and 100 trillion years in the future. This is a vast span of time, but in the context of the full timeline of the universe, including the degenerate era, the black hole era, and the dark era that follow, it is a relatively brief interval, a bright flash in a mostly dark story. We exist within that flash. Not only that, We exist within a particularly favorable portion of that flash. The universe is currently at a stage where star formation, while declining, still produces occasional new stars. The interstellar medium is still rich enough in gas to support stellar birth in some regions. The generation of stars that formed in the last few billion years, including the Sun, includes stars that are warm enough and stable enough to support the complex chemistry that allows planets to be hospitable to life. The cosmic background radiation has cooled enough that the universe is no longer opaque to light, but has not yet cooled so much that useful energy gradients are impossible to maintain. The conditions of the universe today, in other words, are extraordinarily favorable for the existence of something like us. Not because the universe was designed with us in mind. There is no evidence for that, and the universe's behavior over the vast majority of its timeline is entirely indifferent to biology. But because we are a product of those conditions, life, as we know it, requires the kind of energy flows and chemical complexity that only the stellar era provides. We are, in a very direct sense, children of this moment in the universe's history. The atoms that make up your body were forged in stars. The energy that allows your neurons to fire comes, ultimately, from the sun's nuclear fusion. The oxygen you breathe was produced inside a star that died before our solar system formed and scattered across space in a supernova that you could not have witnessed, but whose products made your existence possible. Every human body is, quite literally, a collection of stellar remnants that has temporarily organized itself into a form capable of wondering about its own origin. That is not a small thing. It is, in fact, one of the most remarkable things in the known universe. There is a question that arises naturally from everything we have discussed, and it was articulated most famously by the physicist Enrico Fermi in a casual conversation at Los Alamos in 1950. If the universe is so vast, so old, and so full of stars, many of them older than the Sun by billions of years, many of them surrounded by planets, then where is everyone? The Fermi paradox, as it has come to be called, is not the subject of this documentary. But the journey we have taken through the deep future of the universe gives the Fermi question a new dimension that is worth noticing. If life can arise and persist around red dwarf stars, and we have reason to think this is possible, though not certain, then the overwhelming majority of the universe's biological story may be ahead of it rather than behind it. The stars that will support life for the longest periods of time are the ones that are burning most quietly, most patiently in the current universe. If some form of complexity or intelligence arises around a red dwarf with a 10 trillion year lifespan, the time available to that civilization dwarfs everything in our own experience by a factor so large it becomes meaningless to compare. There are red dwarf systems in our galaxy right now. Proxima Centauri, the closest star to the Sun, a red dwarf at a distance of about 4.24 light-years, has at least 2 confirmed planets. Proxima b, discovered in 2016, orbits within the star's habitable zone. We do not know whether Proxima b has an atmosphere suitable for life. We do not know whether it has liquid water. We do not know whether it's tidal locking to Proxima Centauri, which likely keeps one face always toward the star, and one always in darkness, creates conditions compatible with biology. What we know is that the conditions for life to potentially exist are not obviously excluded. Proxima Centauri will burn for approximately 4 trillion years. if life arises on Proxima b or on any of the other red dwarf planets that current surveys suggest are common throughout the galaxy, it will have access to an energy source that outlasts the Sun by a factor of nearly 1,000. The universe's biological story, if it has one, may be just beginning. We have come a long way in this documentary. We began with a single image, the last star in the universe, dimming and cooling in a darkness so complete that nothing warm exists anywhere within the reach of physics. We followed that image backward in time to understand how the universe came to produce stars in the first place, and then forward in time through the slow decline of stellar populations to understand how the era of stars ends. We have stood at the edge of something that no human being will ever directly witness, the final extinction of the last stellar fire, and tried to understand what it means. And now, with all of that in mind, let us return to the fire we know. Tonight, or on whatever clear night comes next, there will be stars overhead. They will rise in the east as the Earth rotates, arc across the sky, and set in the west. The same ancient, reliable motion that has provided a backdrop to every human life and every human civilization in history. The constellations will be recognizable, because stars move so slowly relative to human lifetimes that the patterns established by ancient astronomers remain essentially intact today. Those stars are burning. Right now, in this moment, nuclear reactions are occurring inside them at rates that would be incomprehensible if translated to human scales. The light you see left those stars years ago, or decades ago, or thousands of years ago. The sun's light left it 8 minutes ago. The light from the Andromeda galaxy, visible as a faint smear in the night sky from a dark location, left it approximately 2.5 million years ago, before the first members of our genus had yet evolved. The universe you can see from Earth on a clear night spans an enormous range of cosmic history. Every point of light represents a different moment in the past, a different distance, a different stage of stellar evolution. The night sky is not a snapshot of a single moment. It is a three-dimensional archive of the universe's history, presented to anyone who stands outside and looks up. And somewhere out there, in the galaxy, right now, this moment, there are red dwarfs burning, quiet, dim, patient, unspectacular, outlasting everything around them, maintaining their slow nuclear fires against the pull of gravity, second by second, exactly as they have been doing for billions of years, and will continue doing for trillions more. One of those red dwarfs, we cannot know which, will be the last. What is a star worth? Not in any economic or instrumental sense, not in terms of what it provides for the planets around it, though that is considerable. The sun provides every photon of energy that has ever driven a biological process on Earth, every joule of energy that built every civilization, every calorie that sustained every organism that has ever lived here, but worth in a deeper sense, in the sense that asks, what does it mean that this thing exists? A star is a concentration of matter that has organized itself through the operation of gravity and nuclear physics into a configuration that produces light and heat and the raw material for everything more complex than hydrogen and helium. No intelligence directed this process. No purpose guides it. A star burns because the laws of physics, operating on the conditions present in a cloud of collapsing gas, produce fusion. It is automatic, impersonal, and has been happening continuously somewhere in the universe for the majority of cosmic history. And yet, the light from a star crosses interstellar space and falls on a planet's surface, warming it. The warmth drives the evaporation of water. The water condenses and falls as rain. The rain collects in pools and rivers and oceans. In those oceans, under the energy of that same starlight, chemistry begins. Simple molecules form complex ones. Complex molecules begin to replicate. Replication introduces variation. Variation introduces selection. Over hundreds of millions of years, selection produces eyes. Those eyes point upward, toward the star that made them possible, and something that might be called recognition occurs. A star, in the fullness of its implications, is not just a ball of burning gas. It is the prerequisite for everything, for complexity, for chemistry, for the exquisitely improbable process by which matter comes to look at itself. This is what the last star's death truly means. It is not the death of a single astronomical object. It is the final closing of the chapter in which the universe contained the conditions for the emergence of new complexity. After the last star, the universe still exists. For a very long time, it still exists. But it can no longer produce new chemistry. It can no longer provide new energy to drive biological or cognitive or any other form of organized complexity. Whatever has arisen in the universe, by the time the last star dies, is the last that ever will arise. The universe, after the last star, has said everything it is capable of saying. There is a tendency, when confronted with information about the deep future of the universe, to feel something like insignificance. We are small. Our civilization is young. The timescales on which stars burn and black holes evaporate make human history. All of it, from the first stone tool to the current moment, seem like a single heartbeat in an endless ocean of time. But insignificance is one interpretation. There is another. We exist during the universe's stellar era, during the brief, bright, energetically rich interval, when stars burn, and planets are warm, and chemistry is complex. We exist, furthermore, at a moment when a species has developed the cognitive tools to understand, at least approximately, the full story of the universe from its beginning to its end. We can trace the origin of the atoms in our bodies to stellar nucleosynthesis. We can calculate, approximately, when the last star will die. We can describe, using physics and mathematics, a future that no observer will ever directly witness. That is not insignificance. It is, if anything, its opposite. It is the universe achieving, through the mechanism of biology and cognition, the capacity to know itself. A star cannot know that it will die. A black hole cannot comprehend its own eventual evaporation. But a species that evolved on a warm planet around an average star in an unremarkable galaxy can, in principle, trace the entire arc of cosmic history. That capacity is extraordinary. Not because it gives us power over the universe. It does not. Not because it allows us to change the fate of the stars. It does not. But because it represents something genuinely remarkable in the universe's history. A form of matter that can observe, reason, and understand. The fact that this capacity is temporary, that we exist in the brief stellar era, that our civilization and our species will someday be gone, that even the atoms of our bodies will eventually be dispersed into the dark, does not diminish what is true right now. The stars are burning now. The universe is here now in its middle period, full of fire and complexity and the conditions for all of it. Now is when we get to be alive in a universe with stars. Let us return one final time to the image we began with, the last star in the universe. It is burning in a darkness so complete that there is no other source of light within any observable distance. The universe has been mostly dark for a very long time. The galaxies have merged and diffused. The white dwarfs have cooled to invisibility. The neutron stars pulse at radio frequencies too long and too faint for anyone to detect. The black holes are still present. Huge, quiet, patient, but they will not evaporate for an incomparably longer time. The last star is burning. It has been burning for longer than any human concept of time can grasp. Its surface is cool and dark red. Its light, if there were eyes to see it, would fall on whatever surrounds it with the quality of deep twilight. Warm, red, just barely bright enough to call light rather than heat. What is remarkable about this star is not its size, or its brightness, or its history. What is remarkable is the fact of its burning at all. The fact that in a universe that has been moving toward darkness and stillness and maximum entropy for its entire existence, this one small object is still in defiance of everything, converting hydrogen into helium and releasing energy in the process. It is not defiance, of course, it is physics. The star burns because that is what a star of its mass, with hydrogen still available, does. It is not heroic, it does not know, it simply burns. And when it stops burning, when the last hydrogen nucleus fuses with the last partner and the last reaction occurs, and the fusion ceases, the universe will have entered a state it will never leave. Not darkness in the temporary sense of a power outage, or in the practical sense of a space between galaxies, but darkness in the final sense, the universe's stock of nuclear fuel, accumulated in the Big Bang and depleted across 100 trillion years of stellar burning, will be spent. The stars will be over, but the universe will continue. Patient, cold, expanding, dark, and operating according to the same laws that made the stars possible in the first place. Somewhere in the quantum fabric of space-time, the mathematical relationships that govern particles and fields and the curvature of space will persist, unchanged, indifferent, and in some sense eternal. The laws of physics do not go out when the stars go out. And perhaps that is the most profound thought we can end with. The universe that contains stars and the universe that has moved beyond them are governed by the same mathematics, the same equations that describe nuclear fusion. The process that lights the stars also describe the Hawking radiation that will eventually evaporate the black holes. The same thermodynamics that drives the increase of entropy through the stellar era also governs the slow settling of the universe into its final dark state. The universe does not change its nature when the last star dies. It simply moves to the next chapter of a story that has been unfolding since the Big Bang, and that will continue unfolding for longer than we have words to describe. We are in one of the early chapters, and we have somehow managed to read the whole book. On a clear night, find a dark place. Let your eyes adjust. Let the stars appear, slowly at first, then more and more, until the sky fills with more light than you realized it contained. Now, knowing what you know, that each point of light is a nuclear furnace converting mass into energy, that the most brilliant stars you can see are the ones closest to their endings, that scattered among those brilliant ones are the dim, patient red dwarfs that will outlast everything else, that the hydrogen burning in those stars tonight will never be hydrogen again, that the light reaching your eyes left its source before you were born, before civilizations rose and fell, before continents moved to their current positions. Knowing all of that, look up. The stellar era is in progress. the universe is still burning, still producing the energy that makes warmth possible, that makes chemistry possible, that makes the specific and improbable configuration of matter that is you possible. Somewhere out there, the last star has not yet been born. The hydrogen that will fuel it is still drifting through interstellar space, decades or centuries or millennia from its eventual collapse into fusion. The story of the stars is still in its middle chapters, and somewhere in this moment, in these specific and temporary conditions of a universe that is still producing starlight, there is a civilization asking questions, looking outward across impossible distances, tracing the arc of cosmic time from its beginning to its projected end, understanding, as well as any form of matter has ever understood anything, the nature of the universe it finds itself inside. That is not a small thing. It may, in fact, be the most remarkable thing in the universe's history so far. The universe knowing itself, briefly, in the light of its own stars. The last star will one day go out, but tonight, the stars are burning,